Welcome to the second of two videos for integration examples. This is section 13.1 and 13.2 in your text. If you haven't watched the theory, which is the first video for integration, you might want to check that out. So we'll be doing two integration examples. The first of which is we have a region R defined where x's values from 0 to pi, y varies from 0 to sine of x, and the surface is given by f of xy equals y. And our goal is to find the volume under the surface f of xy over the region R. So whenever you have these problems, it's always a good idea to draw a picture of the region if you can, to visualize which way to best represent your rectangles. So this is in the xy plane. So we know that y goes from 0. This is y equals 0, the line y equals 0 here. And y has sine of x as one of its curves. And 0 to pi is the bounding markers for x. So we know our region R is just this upper interval, sorry, this upper area here. That's our region R that we care about. And so when we're thinking about which way is appropriate to draw our rectangles, if we draw our rectangles vertically, we have different curves for our start and our stop points on our rectangle. Versus if we drew our rectangles horizontally, the curve y equals sine of x would be both at the start and the stop of our rectangles, which makes it less than ideal. So when we're thinking about this, if we look at Houdini's theorem, we have our x is constant, so that should be on the outside of our curve or our function or our region, and y has a function of x, so y must be integration with respect to y must occur before the integration with respect to x, because y is a function of x. So if we make a note of that, we know that y is a function of x. So that means that we have to have x after y in our integration order. So x goes from 0 to pi, y goes from 0 to sine of x, and our function is y. We go from dy dx here. So as we integrate this, we see that our inner function is from 0 to sine of x, y dy. This gives us y squared over 2, evaluated from 0 to sine of x, which gives us sine squared of x over 2. An important trig identity is that 1/2 sine squared, or excuse me, sine of x squared, so or sine squared of x if you prefer, is equal to 1/2 1 minus cosine of 2x. This makes it easier, this double angle identity makes it easier to use a u substitution later. So this means that our outside integral looks like the integral from 0 to pi. This is our x bounds of 1/2 times the quantity 1/2 times 1 minus cosine x, or sorry, excuse me, cosine 2x dx. This inner piece here, this is our inside 1/2 sine squared of x. Excuse me, that's just our sine squared of x. The 1/2 hangs out front. So let's clean this up a little bit. So we get from 0 to pi. We get 1/4 minus 1/4 cosine of 2x dx. So this is an easy function to integrate. The first piece we have is 1/4 x, evaluated from 0 to pi. The second piece, we can pull out the 1/4 integral from 0 to pi of cosine of 2x dx. This needs a u substitution, so if we let u equal 2x, du is equal to 1/2, is equal to 2 dx. So that means 1/2 du is equal to dx. So the integral, we would have, evaluated for this, we'd have pi over 4 for the first component minus 1/4 If we do our side work on the side here, the integral of cosine of u times 1/2 du is equal to 1/2 sine of u, which we substitute back in, we get 1/2 sine of 2x. We get the integral of 1/4 times 1/2 sine of 2x, evaluated from 0 to pi. Sine of 2 times pi is 0. Sine of 2 times 0 is still 0. So we get pi over 4 as the answer. So the double integral over our region R of the function y with respect to our area is equal to pi over 4. So the area of the surface, or excuse me, the volume of the surface over that region is equal to pi over 4. So let's take a look at the next problem. So given R as a triangular region below, find the volume under the surface, f of xy equals 2 times x times y. So the triangular region is given as bounded by x equals 0. That's this right-hand bound here. Y equals 0 is the lower bound, and the line y minus x equals 2 is the hypotenuse of the triangle that goes between -2, 0 to 0, 2. There are obviously two ways to set up this region. We can set it up either with horizontal rectangles or with vertical rectangles. So if we set it up with vertical rectangles first, we know that we have to rewrite, so our x values here, our x bounds go between -2 and 0 because our x's are not changing, and our y bounds have to go between 0, and then solving the hypotenuse as a function of y, we get 0 to 2 plus x, or x plus 2 if you prefer. And so this means that our integral looks like -2 to 0, 0 to x plus 2 of the surface 2xy dy dx. So solving this integral, the inner part, we have 0 to x plus 2 of 2 x y dy. So this gives us xy squared evaluated from 0 to x plus 2, which gives us x times x plus 2 quantity squared minus x times 0, so we get this piece. You can leave it as this, or you can distribute this out. So you get x times x squared plus 4x plus 4, which gives us x cubed plus 4x squared plus 4x. With small polynomials like this, it's often easy to distribute this out because this makes the outer integral easy to evaluate. So -2 to 0 of x cubed plus 4x squared plus 4x dx makes this integral 1/4 x to the 4th plus 4/3 x cubed plus plus 2x squared evaluated from -2 to 0, which gives us 2, 4, 8, 16 over 4 is 4 plus, let's see, that's going to turn into a, let's see, so this will be negative quantity 4 minus 2, 4, 8 times 4 is 32 over 3 plus 2, 4, 8. So this turns into -4. See here, 4 plus 8 is 12. So -12 plus 32 over 3 as our final answer. So note, we could have done the bounds horizontally. So if we had done horizontal bounds here, we would have let y vary from 0 to 2 and x varies from y minus 2 to 0, and we could have set the integral up as 0 to 2, y minus 2 to 0, 2xy dx dy, and by Houdini's theorem, we would have gotten the same integral. So it depends on what you're more comfortable with, horizontal rectangles or vertical rectangles in this case. So the next video in the series will be introducing polar coordinates and introducing an integral where polar coordinates makes your life much easier. If you have any questions, always feel free, email me or visit me in virtual office hours.